Welcome back to General Chemistry. We're going to be talking about changes in substances that depend on temperature. We'll call those phase changes, thinking that the phase is going to distinguish between liquid, solid, and gas. And remember that these physical states depend on what is the kinetic energy of the molecules, and the kinetic energy in terms depends on the temperature. So we're going to be looking at these things as we move on. So first let us remember that we're talking about intermolecular forces. Intermolecular forces. So it's between molecules, and this can be because the molecules are polar, so the polarity polar, so they can be polar. Okay, we're thinking about polar molecules. They can be non-polar, so we're dealing with in this case we call this dispersion forces. You can have ionic, and we'll talk about one later on that we call hydrogen bonding. And this is kind of a misleading name because it's not a true bond in the way that we have been talking before. But anyways, that's something that we'll talk about later on. So thinking about a substance that can be in the solid form, can be in the liquid form, or it can be in the gas form, we see that as we talk in class that these shapes, these phases, these physical states depend on the interaction between the molecules as they are in that particular state. And we know that as we increase the kinetic energy by, for instance, adding heat, we'll get to a more disorganized arrangement of the molecules. So in this case, they are loose enough that they will not continue having the shape that they had before, but now they are somehow acquiring the shape that is given by the container. But one thing that we see is that the total volume that the solid had before is very similar to the volume that the liquid has. But if we continue now adding more heat, what we know is that the liquid is now going to change into a gas, and now the molecules that we see here are completely separated, and they will not have the same volume. Now the volume is going to be given by the container over here. So this is what we are now looking at. One of the things that we mentioned in class is that the gas doesn't have a shape, that the gas is going to be spreading all over the volume available in that container. And of course, if we have an open container, then the gas might escape as well. So this is something that we know. The other thing we can see here in this plot is when we look at the temperature at which a substance boils, that temperature is called the boiling point. So point here is talking about the temperature. So when we're thinking about temperature, we're thinking about at what point this liquid, for instance, the heptane here that has 7 carbon in the molecule, is going to start to boil. And we see here that there is a dependence of the molar mass with the temperature of boiling, with the boiling point. The heavier the molecule, you have more surface, as we talk in class, for the dispersion forces to act, and therefore the molecule will be able to cohere better because it's bigger. So in this case, it's very clear how the molecule structure is going to determine the intermolecular forces. And of course, we know that if we have even smaller molecules, like if we go to the methane, which we know is gas at room temperature, then you're going to be talking at a much lower boiling point for the methane, and so on. So there is something that you can see is that evaporation has the opposite process that we call condensation. They are similar in a way, but not exactly the same. they do occur in opposite direction. One would be the evaporation when you are heating in general and heating, and the other one is when you are cooling down. So cooling, or the other way that we use for condensation would be freezing. So you are lowering the temperature there. Now the main difference with the two would be depending on what kind of container do we have. If you have an open container, then the problem with the vapor is that it might escape, right? So as they can spread out of the container, then you have a lower rate of condensation. So the net result is that the rate of vaporization is normally greater than the rate of condensation. But if you have a closed container, then things are different, because now the vapor is not allowed to escape, and then you have that the process of condensation is about the same rate as the evaporation. So those are kind of the things that we have to take into account as we're dealing with the loss or gain of a substance as it evaporates or condenses. So the question here is, how do we measure the amount of energy that is required to change phase? So let's think about vaporization, and we will call that energy the heat of vaporization. And of course the word heat here is related to the energy required. Now if that heat is at constant pressure, remember that we call that the enthalpy. So many times we call the heat of vaporization the enthalpy of vaporization, or you can also find in some texts that they talk the enthalpy of evaporation. So that would be the other way of looking at the energy required to make a liquid go into a gas. So in this case, you always need energy to give the kinetic energy to the molecule. So this process is always endothermic. So the delta H of vaporization is positive. Now the delta H, remember, is the symbol that we are using for enthalpy. So we're talking about enthalpy here, and that's what we call the delta H. And these are some of the values that you have for different molecules. Like for instance, think about water there. When you evaporate water at the boiling point, that would be about 100 degrees Celsius, you need about 40.7 kilojoules per mole of energy to evaporate that. Now that is different if you are dealing with the evaporation at a lower temperature. So for instance, if you are trying to evaporate something at 25 degrees, then the water will evaporate anyways. We know that if you put something to dry, by the drying is a process that normally occurs under 100 degrees Celsius. But then you need more energy. In this case, for water, we're talking about 44 kilojoules per mole to evaporate water at, let's say, room temperature, 25 degrees. So the question that we have to ask now is, what amount of energy do we need to go through the whole process? Let's say that we have very cold ice over here, and we're going to bring it to a vapor over here, right? So we want to produce vapor from ice. Well, the first thing we mentioned this morning was that the ice has to go up to the freezing point or melting point, which is 0 Celsius over here, and that would be the warming of the ice. And of course, this increase over here will only depend on the heat capacity. So here you have the heat capacity of the ice, and depending on the amount of ice, you will need that energy. So let's say that we are now talking about 1 mole of ice. So the amount of heat required for 1 mole of ice would be about, we see here, about 0.941 kilojoules, right? And then the next step is to melt the ice, and the ice now requires energy to, we talked about before, the enthalpy of melting. That would be the energy in this segment over here, which if we're looking at per mole, then we're talking about 6 kilojoules per mole, and this would be only related to the delta or delta H of evaporation of melting, right? So we're talking about the delta H of melting here in this segment over here. Now the next segment, let me clean my plot here. Let me get rid of that. So the next thing would be to look at what happens once we have water. And of course, once we have all the ice melted, then the water is going to increase the temperature, and you have the water becoming warmer and warmer and warmer until you get to the 100 degrees Celsius, which is the boiling point of water, right? And at that moment, the temperature stops increasing because all the excess energy that you are putting from this point onwards is going to go into the evaporization of the water, right? So this energy here that we are using here, this is going to be the delta H of vaporization, right? Of evaporation. So this amount of energy you can see is greater than the amount of energy of melting here. Why would that be? Let's keep that question in mind. And then the later stage, of course, is once you have evaporated all the water, you get to this point. Now the vapor starts to increase in temperature, and this part over here will only depend on the heat capacity. We call it the C, remember, of vapor, to see how much increases there. So let me again clean this plot here and to revise a point here. Well, the question that I asked before about why is that I have more energy involved here in the evaporation of the water than here in the melting of the ice is because if you remember, the difference between a liquid and a solid is not so big. I mean, the molecules are moving, but are moving at this within the same volume. While if you remember, the gas molecules in relationship with the liquid are moving at a much faster rate here, so they require much more energy. So the process of evaporation here is much higher. So you require higher level of energy to go from liquid to a gas than you require to go from a solid to a liquid form, right? So that's the reason that you have that there. Anyway, so I'm going to stop here, and we'll calculate this for different amounts of ice later on in class.